Well, thank you very much. Thank you, Gosha. Thank you, all the other organizers for having me. And it's very exciting to be on your online seminar in 3 cities simultaneously. Okay, so I'll talk about joint work with Asaf Weinstein, who is from Hebrew University. He's also online to help me and answer questions. So I'll begin. Oh, why does it move?
So Danny, just one
Oh,
question. Is it
yes.
okay for you to take questions during the talk, or do you?
Yes, definitely. Yes, of course. Of course. Okay. So as I've said on the abstract, to make things as clear and concrete as possible, in all the notations in the example, I'll be talking about one particular high-dimensional logistic regression example, but the methodology I will present is very general. It can be applied to any high dimension. It works well for high-dimensional problems for any arbitrary likelihood. Of course, in our case, it works better or worse, but the ideas are quite generalizable to any high-dimensional problem. But I'll only talk about this because I think it's a more concrete, very relatively simple example. Okay. So first of all, I'll present this high dimensional problem example. Then I'll try to, because what we're actually suggesting is kind of strange sounding, I'll show that it's actually not very far-fetched and very close to other things that have been appeared in the literature at some time during the second half of the 20th century. Okay, so it's maybe not run-of-the-mill kind of ordinary stuff, but it's not totally contrived. Okay, so that will be the background. And then I'll talk about this oracle-based optimal inference. And I'll show what does this mean for a Bayesian perspective. And then it is a Bayesian construct. And then also show that this Bayesian construct actually has very, very good frequentist properties, okay? And then this is this oracle thing, which is by definition, definition theoretical. And then I'll show how we actually implement it, okay? And the implementation will be through hierarchical Bayes modeling, which also has very good practical properties, and it gives very good approximations to this theoretical construct. And then I'll show simulation results, okay? And then discussion. The talk will be kind of, I only have like 20 slides and only 10 are like difficult slides. So I want to go through them as slowly as possible. So please ask questions if anything is not well understood, or even let's not try to, maybe the bar will not be well understood, but kind of understood, okay? So bear with me, okay? I don't really understand everything. I don't even think that Asaf understands everything. So we'll see. I was kind of surprised by some of my newer slides. Okay. So this is the example we will be thinking of in this talk. It's a high dimensional logistic regression. We have a fixed parameter vector. We have a beta, which is fixed a priori. We know this fixed beta. Okay, we have a fixed X matrix. Where here, the idea is we just generate this X matrix is not something real. We just generate it by IID 1 over n entries. Okay. Then we have this response vector. The only random part of our model is this Y, this response, which is a logistic. We have a vector of mu's given by X beta. And then we have this inverse logic transform. And then each of the Y's is Bernoulli with this Q, this probability Qj, okay? Why am I calling it high dimension? Or why isn't this a regular logistic regression? Because this is on a big scale. The beta vector has 800 components, and the response vector has 4,000 components, okay? So it's a big design matrix. It's not huge, but it's big. It has 4,000 rows, 800 columns, and each of the 4,000 responses has something to do with the vector of the betas, okay? So it's a non-sequence model in the sense that all the betas contribute to each of the responses, okay? So it's kind of a difficult likelihood. It's in a sequence model by simplicity, we'd have an orthogonal X matrix, and each of the responses corresponds to one of the parameters, okay? In this case, it's a simple model, but it's like the simplest complicated model. Think of it like this, okay? So the model is clear? Okay, just, okay.
Sure, yeah.
Okay, so let's move on. Okay, what we're showing is connected to lots of things in the literature. First of all, our main competitors are these regularized estimation methods, which actually corresponds to eliciting a prior or shrinkage prior to the model parameters, okay? What we're actually doing looks like a ridge regression, looks like a lasso, looks like a spike and slope, and even goes like an A-B slope, okay?
Yes, yes,
okay, the idea we have an explicit prior at the other part of it, okay? So we assume the parameters have this, the idea we're shrinking, we have a prior on the parameters, but the idea we're not eliciting it, we're estimating it, okay? So what it is, it's empirical based, okay? So empirical basis has been with us for a long time, since the 1950s, Robbins, James Stein, Brown, etc., etc. It looks like Efron's work for the FDR in the sense that he's saying, look, I want to estimate pi naught, okay, which is like the prior, it's the distribution of the parameters, but in his case of like Efron's work, it's a two-group model. Here we have like a general one-dimensional distribution, okay? And some of our work is also connected to work by Larry Brown, Eitan Greenstein, etc., etc. Okay. What are actually flavor in empirical base is like the compound decision approach, beginning with Robbins, Zhang, this is Kunwi Zhang, Asaf's work with Kunwi and Larry Brown, where the idea, and this is like our main machinery, is that they show that Robbins has showed that for sequence model likelihood, which is what I've talked to you about, and compound loss, a compound loss is like all the losses are compound. It's like a sum of square loss, a sum of individual losses kind of loss for the entire vector. Bayes rules with respect to the empirical distribution of the parameter vector minimize risk for any fixed parameter vector. This is very, very nice theoretical results from Robbins. Okay, and this for us, for Asaf and me, this is like the main motivation is why we would want to think about Bayes rules in high dimensional problems. Okay, so this is our main motivation. But this motivation is kind of limited. First of all, everything is theoretical, even ours, and it only holds for the sequence model. We're thinking about the non-sequence model, okay, which is all the regular cases in real high dimensional stuff are non-sequence model, okay? So this is what we're actually talking about. Extensions of Robbins's compound decision approach, okay? And our machinery, we have the theoretical stuff and our machinery. Our machinery is hierarchical-based modeling, which we use a finite Polya tree on dyadic partitions to define random distribution. This is an idea that I took, from Ferguson. I copied it. I didn't even know. I heard it somewhere and then I forgot. And then people reminded, look, what you're doing is actually Ferguson's idea. And it is a finite Polya tree. Okay, so this is the methodology, and I've been using it like the last 10 years for everything. Like everything I do is with it has a finite Polya tree on the other side. Okay, so this would be the implementation stuff. The main theoretical oracle would be an extension of Robbins's idea, and the implementation at the end would be a Polya tree. Okay. So this is the background, and now I'll begin with the actual stuff. Okay.
Danny, maybe I'll just comment
Yes,
that
please. Yes.
I mean, maybe you purposely postponed this, but just so it's clear, the transition between maybe the model and the last two slides, we're trying to somehow optimally estimate beta or something like that, just so it's clear.
Yes, yes. It'll be now. I'll talk about what we actually want to do. Okay. Okay. So as I said, this is a regular standard high dimensional problem. We have beta. We want to estimate this parameter vector beta, and we want to do it optimally as well as possible. And we want to do it like in a frequentist sense. For each fixed value of beta, we want to figure out what is a good estimation scheme, okay? And Emily doesn't work. This is like the gist of Pragya's and Immanuel's, paper. They said, look, the Emily doesn't work, and it's even biased, I guess, right? This is the main idea, that like it's maybe asymptotically unbiased, but actually it is biased, and it's bad. Let's unbias it and improve it a little. The case is that if you do like Lasso, you can improve it a lot. And if you do our stuff, you improve it even more, because we have the optimal shrinkage. This is like the gist of what we do. And so let's start from the Bayesian perspective. To run a Bayesian procedure about beta, not hierarchical, right? We need to have a prior for the parameter vector, okay? Conditioning on the observed y, we can have a posterior distribution, the conditional distribution of vector beta given the data, which is proportional to our prior and beta times the likelihood, okay? And then for whichever loss function we're be interested in, our right loss function, it's the loss between our estimator beta hat and the actual value of beta vector. Then the Bayes rule is given by, this would be my Bayes rule. It will be the argmin, it will be the estimator of beta that minimize the posterior expected loss. Okay, this is the textbook regular Bayesian stuff. And per definition, this Bayes rule minimizes the average risk. Okay, nothing new until now. Okay, I can proceed. Okay. Suppose we have extra information. Someone whispers in our ear, the parameter order statistic. This is not the data order statistic. This is the parameter. The data order statistic we can easily compute. This is the parameter order statistic, which no one will actually knows. But theoretically, let's say we do it, we'll call it an oracle. Someone tells us not the actual value of the parameter vector, but its order statistic, which is less good. But still, it's lots of information. We'll denote this by beta vector ord, okay? And it's like the order statistic. And agree with me that knowing this is equivalent to knowing the empirical distribution of beta, okay? I don't know what is beta 1, beta 2, beta 2, 3, etc. But I know the smallest beta, the second smallest, etc. So I know it's marginal distribution, it's empirical distribution. If I'm a Bayesian, I can call it the empirical distribution because the distribution itself is, beta itself is random, okay? And this is the entire trick from a Bayesian perspective. Conditioning on y and on beta ord yields better Bayes rules. The idea, if I have more information, I get better Bayes rules. And I'll just elaborate on that. Given y and beta ord, we may derive the conditional distribution of beta vector given y vector and this order statistics. And the Bayes rule may now be derived as following. The idea that I use the same notation. It's beta hat Bayes, which is a Bayes rule. It's a function of y, but I'm also assuming that I know beta ord, okay? So it may or may not be a function of beta ord, but the idea that's the argmin, it's the estimator that it's based on y that assumes knowledge of beta ord. And what I need to maximize is the different posterior expected loss. It's the expectation of beta, where I take beta from its conditional distribution, not beta given y, but rather beta given y and beta ord, okay? And then the same, it's the loss, but it's a loss for the different estimator, okay? So what I'm doing different, I'm computing a slightly different posterior distribution. I'm conditioning on y and on beta ord, okay? And why is this better? Because I can express the average risk before. This is the average risk. The average risk is the same, but the idea that I can write it differently, it's the expectation over the marginal distribution of y and of beta ord for this conditional expectation. Because this conditional expectation assumes I'm conditioning on y on beta, once I condition on more, I can assume like my function is of more stuff, and therefore I can have a smaller average risk, okay? Okay, the idea that I'm looking for my base rule in like a more finer scale. I can take my base rule as a function both of y and of beta ord. So by definition, I can improve on my base rule. How am I improving? Because my average risk may be smaller, okay? This is standard trickery, Bayesian trickery, okay? So now let's try to unpack what is this distribution, okay? What is pi of beta given y and the order statistic, okay? Let's unpack it. So to do this, we need permutations. We denote by this calligraphic P the set of permutations of 1 to n, the set of permutation on m objects. And what are, of course, these m objects? The parameter vector, okay? This means that for all beta, for all fixed, in this case, beta is like the fixed beta, but it works for any beta. I mean, for any fixed beta, there is this I use throughout this tau, how do you call it? Tau, tau
prime.
Tau prime, okay. This tau prime is this particular permutation of beta ord that gives me this beta fixed vector, okay? So tau prime throughout this talk will be the same guy that gives me beta. So I can write beta vector as tau prime of beta ord, okay? And the nice thing that this pi specifies a distribution on these order statistics and also on these permutation. In what sense? We can think of a density on order statistics. What is the density for getting this order statistic? I just sum the densities for the entire permutations of beta, okay? This is this. And also I can think of a conditional distribution of one particular permutation given beta ord, which is just, what is this density, prior density of seeing this particular permutation of beta given the entire set of order statistics, okay? So this is a distribution I can analytically think about and derive. And then we can express this. What is this thing we're interested in? This conditional distribution, posterior distribution of this particular ordering given the data and given this order statistic. This is the standard way of deriving it. This is like a conditional density. So I'll be very loose with the notation, sometimes F, sometimes pi, but I think you'll get the meaning. So this is the joint density of getting beta and y and the order statistic. And this is the thing I'm conditioning on, okay? The idea that if I'm thinking, I also know beta and I also know beta ord, once I know beta, I also know beta ord, so I can rule out this. And then it's just a joint distribution, and instead of writing beta vec, I call it like this, okay? So this is what we get in the numerator. In the denominator, I'm just summing up the same thing over all the different permutations, okay? And here I'm just writing it nicer, okay? The idea that I write, this is like, I'm writing it nicer instead of like, I'm saying, what is the distribution, the density of both these two events? It's just I'm conditioning on theta hat, and then I'm writing it like this. It's an easier way of writing. Okay, so if we want to know what is this posterior distribution, we need to know the likelihood for each possible configuration, permutation of beta, and also we need to know what is the prior distribution, the prior density for each of the m factorial different permutations, okay? So this is the most general way of thinking about it. But let's say we have symmetric priors. I mean, why not have symmetric priors? What do I mean in symmetric priors? For cases in which all beta order are a priori equally probable, we can make this much simpler. Does this make sense? The idea that in some cases it makes sense, in some cases it doesn't make sense. To be on the safe side, notice that in all the shrinkage prior, not only are the components of beta symmetric, are the beta vectors symmetric, they're a priori IID. That means they're independent, okay? So all the shrinkage priors, what do we assume? That the beta components are asymmetric. When we think about what is an MLE, the MLE you could think about, let's use a flat prior, which is also symmetric and IID, even more so. When isn't it symmetric? I mean, if I have some knowledge regarding this problem, then I would have, I mean, by definition, I wouldn't consider them, I would say some of the betas are bigger and some are smaller, and then by definition, it won't be exchangeable. But in cases where I come to the data with this total ignorance, it would make sense to think that all given beta ord, all different permutations are equally likely, okay? So the thing, I'll discuss it in the discussion, we'll get back to that. Okay, so what happens in this case? This conditional distribution for each of the permutation given the vector, which we've defined like this, because all these guys in the sum here and in the numerator are equal, then we're just counting. The idea that this distribution over permutation is a symmetric parameter space. Each of these, the prior probability of each of these given beta ord, the prior of seeing, by definition, of seeing each of these guys is equally probable 1 over n factorial. And then we just get a much, much simpler expression for this conditional distribution of beta given y and beta ord. So it's just, this is something that's very easy to compute. It's on the numerator, we get the density, the likelihood for y when we plug in, the idea for each permutation of theta, the posterior distribution is, on the numerator, we get the likelihood for this particular permutation of the beta vector, and in the numerator, the sums of the likelihood for all m factorial permutations of beta. And what's the nice thing? What don't we have here? We don't have anything from our original pi. Once pi is invariant, is symmetric, it doesn't matter what pi is. That means whichever prior you may use in your shrinkage philosophy, once you condition on beta ord, consider if it's symmetric, it doesn't play a part. We can always improve on it by just throwing it away, okay?
Yeah, Danny, let's maybe just emphasize this point.
Yes, please emphasize.
I'm sorry to.
No, it's good.
I think that's the crucial part, is that as long as the original pi is symmetric and they're like exchangeable, and there are many such pi's. As long as pi is exchangeable, the expression 2, once you condition on beta ord, the expression 2 does not depend on pi, and this is what we capitalize on.
Yes, the idea we don't need to know what pi is. The idea we don't need to, excuse me?
One very simple question. Is symmetric
Yes.
and exchangeable equivalent?
What we actually do is exchangeable. The idea we look at, the idea it's basically it's exchangeable. Symmetric is the idea is what's
I mean,
in this case we actually exchangeable. We write this pi of the entire vector, and when we exchange its components for every permutation, we get the same now. It's exchangeable actually. It's called exchangeable, right, Asaf?
Yeah, giving all equal probabilities to all orderings of beta order is precisely the definition of an exchangeable distribution.
Maybe it should be exchangeable priors and not symmetrical. Maybe it makes sense. It's more, this is how the property is called in English. Okay? But what it actually, I mean, this is what it means. It means that we exchange the ordering of the parameter vector, we get the same prior. Okay?
Yeah, and again, the point is that all the estimators that almost everything that we know, including AB slope and slope, and of course lasso and ridge, and least squares, and everything is like can be expressed like sort, at least in spirit, like a Bayes rule with respect to an exchangeable prior.
Yeah. Okay, so the idea, what we do is like, once we have this extra information, we can get a better Bayes rule, where the amount of how much it's better, of course, is by of course, it depends on the problem. If we have very strong likelihood that the prior doesn't really matter, but if we have like very high signal signal to noise ratio is very small, so we don't get a lot of information, the likelihood, and the elicited prior is very different to the actual marginal distribution of the parameter vector, this improvement will be very, very big, okay? It's always, we have nothing to lose from that, given that we be able to estimate this prior, okay? And just to be for clarity, if we're interested, for example, our loss is this squared error loss, okay? So at least the sum of square loss or whatever, it doesn't really matter. Then we know that the Bayes rule is the posterior mean. So in this case, this oracle posterior mean would be, we know, the idea is we know beta ord, we just don't know how to order it correctly. So the idea, how do we find our Bayes rule? In the numerator, we sum over our different permutations. We take each permutation of the beta vector and we weigh it by the likelihood. And of course, to have something with like, to have the weights equal to 1, sum of the weights equal to 1, we divided we divide by the sum of these weights, okay?
Yeah, and again, the point is that the Bayes rule in the bottom of the slide is simultaneously better than all Bayes rules for any exchangeable prior.
Okay. Okay, so I'll move on. So this was the Bayes case, the Bayesian case. Now let's move on to the frequentist case. Okay. In the frequentist case, in the Bayes case, we assume this beta has this distribution, and the Bayes rule is actually the best case. It minimizes the average risk. The average risk is something that it's not really clear. It's clear if it's actually beta has this distribution. But from a frequentist perspective, it's simpler. We have this fixed unknown beta, and the goal is to minimize the risk. Okay, that's the same risk from the average risk, only now we're interested in this expression for a particular value of beta. And I'll denote it like as the average risk was a small r, okay? The average risk was, where did I write it? The average risk was, where did I write an average risk? I have somewhere an average risk. I'm sorry, I lost my average risk, but the average risk would be a small r, okay, which is only a function of our estimator. A risk is a big R, which is a function of both our estimator and the actual value of beta, okay? And how do I compute it? I take the expectation over my observation when I sample the observations from the condition distribution given the beta, okay? This is like the regular frequentist setup, and I take the expectation of the loss, like a mean square error is like a risk, okay? And to show, what I want to show you is that the average risk I've derived, the Bayes rules I've derived before, which is both a function of y and this order statistics, also yields small risk. So to do so, I'm going all the way back to Robbins's idea, and I'm showing you, I'm considering this made up pair of T and W vector, okay? So what are this pair of T and W vector? T is actually, in this case, is the parameter. I'll call it the parameter, okay? T takes on the values of the m factorial different permutations over m objects, okay? So what is the probability that T is equal to each of these taus? It's 1 over m factorial, okay? W is, in this case, the data, okay? And what is the conditional distribution of W vector given that T is tau? If T equals tau, then I sample W from this likelihood. It's from the function, the data distribution, given that my parameter vector is this particular permutation of beta O, okay? So in this model, I'm sort of like modeling the idea, what does the Bayesian problem look if I know beta ORD, okay? It's not the original Bayesian problem, it's a different Bayesian problem, okay? Because it's easy to see, in this made up example, the posterior distribution that tau equals theta prime, which is our correct distribution, is given that W is Y, is this guy. Do you remember this guy? This guy is the same guy as the posterior distribution in 2, okay? This is the same guy we've had in our problem, okay? If we have the same posterior distribution, okay, and we have the same loss, then we have the same Bayes rule, okay? So this means that the Bayes rule we found before is also the optimal solution for these strange problems on the theta and W's. And what we'll show is that because it's the same problem for the theta and W's, actually has very good frequentist. The idea is we're showing, look, the regular Bayesian solution, it's not really clear if it's a good or bad frequentist solution. But because this general Bayesian solution is also the same solution for this specific contrived strange solution, will show that because it has this property, it also has very good frequentist properties, okay? So this is what I'm doing is an extension of the idea that was presented by Robbins for the non-sequence model, okay? So it's not it's not a new idea, it's an adaptation of the idea by Robbins from 1956, which is an excellent idea. That's why we're going back to it 64 years later, okay? 65 years. Okay, per construction, this Bayes rule we've had before minimizes the average risk for T and W. So let's just write what this average risk is, okay? By definition, an average risk is the risk over the parameter and data of the loss. What is the loss? The same loss we've had before, okay? Whichever loss you want. Let's just write it down. Instead of the expectation of T of W, it's just the expectation of T times the expectation of W given T. So this is clear, okay? What does expectation of T mean, over T mean? T can take all m factorial permutations. So to take expectation over this, we just sum over all permutation, the probability of seeing this particular permutation times the second thing. Well, what is the second thing? That's the expectation of W given T. But W given T is this, I mean, I'm taking expectation, I'm taking W as the parameter vector, the observation vector, given the condition distribution of the data, given this particular permutation of the same object. And look, people, this is the risk. This is the frequentist risk, okay? And this is what I'm writing in. So what it means is that expression 3 implies that this thing, this same Bayes rule minimizes the mean risk over all permutations of beta orders. And I want to point out that this is very different than average risk in 1. So let's go back to see what average risk in 1 was. Where was 1? Okay, this is 1. This is the risk. Okay, I didn't find it before. So when I'm doing a Bayesian, I'm actually minimizing this. And this thing is a very strange looking thing, because I'm taking expectation over all the y's and over different betas. Betas can be a very big thing, okay? I can take betas can look in different, very strange, I mean, the idea that beta vector can be a very wide distribution, having lots of different contrived things, okay? And this is very, very different than this thing, okay? Where is this thing? You see here, beta, I mean, beta doesn't take on very, what does beta change? It's the same order statistic, but what I'm just doing, I'm looking at different permutation. So it's essentially the same problem. I'm just changing the ordering of the betas. And if I have an estimator that works well for all orderings of beta, then it's a very different property than an estimator that works well on average for all the different betas you may have. Can you see that it's a very different criterion? I mean, it's very important for me. Okay? Okay.
Yes.
Oh, okay. In particular, as in our example, what is our example? I have this vector beta, which is fixed. And then the idea that once I have this X matrix, the X matrix, is there, I mean, the idea, we ought to have to, in this particular example, you have to agree with me that if I take a fixed X and a fixed beta, if I take the beta and mix it up, the idea, what am I actually doing? I have X, fixed X and fixed beta, and I'm saying, let's look at the distribution of Y for one particular ordering of beta. This would be this guy. Look at this guy. It's a distribution of Y given one ordering of theta. And let's see how it changes if I change the ordering of beta. But it's a linear model. You have to agree with me that if I change the ordering of beta, I can do the same thing by fixing beta and changing the ordering of x's, right? But all the x's are the same. So that means that the risk will change a little if I change the orderings of x. But if it's like a very big vector of 4,000 x's, they all look about the same. They're exchangeable. So the idea, you have to agree with me that in this case, these guys are not very different, okay?
So I guess here it is important that x's are independent, isn't it?
Yeah, that x's look the same, are exchangeable.
Yeah.
They look at, they're like approximately exchangeable. I mean, here it's not exactly exchangeable. I mean, this is, Asaf is very keen, if I can, to say something more general. But I'm happy with about the same. Okay, the idea, and I mean, if we want to do it, have it more formally. Okay, say like something about. I mean, Nachon Asaf, right, Asaf? But
I think that it's fine to stay with the exchangeable X. The important thing is that if the columns of X are exchangeable,
Yeah.
then changing the order of beta or fixing beta and changing the order of the columns of X is the same.
Yeah.
In
Here, I mean,
distribution, it's the same.
yeah, here in this example, I mean, I just want you to appreciate that it's about exchange, that it's like, it's not, the risk is not exactly the same, but if you actually went around to, it's not easy to compute this stuff, but you'll see that it's almost the same, that it doesn't matter how you order the betas, the risk is the same. Okay, and it's something computable in the idea. Okay, and what does this mean? If we have like a mean of these objects, and each of them is the same, and if we were able to minimize the mean, then then this Bayes rule has a small, I mean, it's not minimal, but it has a small risk for each of these orderings. So, and this is what we want. We want a rule that works well for each of these instances, okay? So this is the frequentist. The idea, in principle, every Bayes rule has this mean property of, I mean, the idea it has a mean, by definition, an average risk is a mean over the risks. But here, the family of risks I'm considering is fairly limited. And this is why I can say that I have something which is good for each particular instances, because the instances are similar, okay? This is why we think our results are also good in a frequentist sense, okay? So this is, okay, so this is clear?
Okay, yes. Mhm.
Okay, so now I can move on to the implementation stuff, okay? Okay, I moved, okay, so I moved on to slides, okay, so this is frequentist perspective. Okay, so now I'm moving on to the implementation part. We have this thing that we want to compute. We want to compute these Bayes rules, these Oracle Bayes rules, and to do this, we have to know the margin distribution of the parameter vector, and we need to do permutations. But we don't know how to do this. I mean, what we actually are able to do, what we're actually doing is we're estimating this marginal distribution. And instead of looking at this, we're doing like IID sampling. And there all this work in the high dimensional problems, doing permutations and IID samples are about the same, okay? So this is what we're actually doing. And the idea that in simulations, we can see that it works well. I mean, this is all I can say at this point. I mean, I have no, I mean, it's like two parts. We have the theory and we have what we're implementing. And empirically, I mean, we don't really yet know how to say how well these approximations actually approximate what we're looking for, okay? And if we go back just to make, like, put things in perspective, yesterday we had a very nice talk about by Nikos, Asaf, what's his last name? Very long Greek name.
Ignatiadis.
Yeah, and he worked with Stefan Wager, and they've been able to like say how good are these functionals, approximation for functions, and they were only working in the sequence models. So no one even has the technology to assess these stuff in the non-sequence model. So now we're just offering methodology and offering motivation for why it should work. Okay, so this is just work in progress. Okay. So what we do is we implement hierarchical Bayes model that approximate this conditional, the posterior distribution of beta given y and given this order statistics in 2, and derives Bayes rules that approximate the Oracle Bayes rule. So this is how we do it. We embed this likelihood in a generative model for the data. The first part of the model, and this is what I'll show next, is we generate this distribution function. What is this distribution function? It should be the marginal distribution. It's not exactly pi of beta. It's like the population distribution from which we sample the betas. I mean, this is like the closest thing of thinking about it, okay? Okay, so, and we have a concrete way of doing it. And this is like the main methodological advancement is part one, okay? How to do part, what part one means is like, so I'll continue. So the idea is we think in our heads that the data was generated as following. First of all, I make up this distribution. This is point one. Point two, I generate the betas IID from this distribution, and then I generate the data from this condition distribution of the data given the beta vector, okay? So this is all made up. This is our imagination. It doesn't work, but we think this is what's going on, okay? And then we use a Gibbs sampler. The idea, we only see the y's, and we use a Gibbs sampler to derive the posterior distribution of the H beta model given the y's, okay?
Sorry, what's the H beta model?
I'll describe it later. H beta model is this model that spews out distribution functions. Okay, it's like you could think of it like as Dirichlet process 2.0.
Okay, thank you.
Okay, the idea, we have something that produces distribution. We take our beta vector IID from this distribution. We take the y's from the conditional distribution of this logistic regression model given the betas, and then we crank our machine. What does our machine do? It derives. I mean, the idea is this machine can have posterior because it's something we can update. We know how to compute we know how to compute the posterior distribution of this thing that makes distributions given the data, and we just crank it and run it again and again and again. Okay, and what happens? In which Gibbs samples of the idea is we sample once we assume that F comes from this beta model, and once we see the data, we know the posterior model. So we use the posterior model to keep on spewing new Fs. What are these Fs? Fs are deconvolution estimates of the distribution of this beta ord, okay? And Gibbs samples of beta vector are approximate posterior samples from this distribution we're interested in, okay? So the idea, we don't know what's going on here, but our machine learns how to estimate, learns its distributions, okay? I'll show it in a minute, okay? I'll show how it looks in a minute, okay? In the next slides. And what are our inferences? Our inferences are base rules for the Gibbs sampling distribution of beta, okay? What is this beta? It's not a real beta. It's the beta that lives in point 2, okay? And the nice thing is that beta that we look at its posterior at point 2 looks very, very similar to these different, this tau of beta we thought about in our Oracle framework, okay? So this is kind of fuzzy, but it's actually very simple. So first of all, what is the hierarchical beta? This L-level hierarchical beta is just a finite polyetry on dyadic partitions of, I take a support, and if I'm interested in it, and then I'm looking at dyadic partitions of the support, I could either cut it into two. I cut it first, I take the entire support, and first I cut it into 2 parts. And then I take each part and cut it into 2 parts, etc., and keep doing it at L levels, okay? And what we use it to model random distribution function with step function probability density, okay? The idea is our objects are not continuous distribution, but step function distribution in which we approximate any continuous distribution. What are the parameters of these models? The model parameters are these independent beta random variables that specify the conditional subinterval probabilities for the dyadic partitions. When I run the model, the prior model is that each of these distributions are uniform 0, 1, which is known as a beta 1, 1. Okay, the idea I begin the model with a beta 1, 1, and how do I get from these beta variables actual probability? I take products of these stuff. Okay, so at the end of the day, what I'm looking up is this step function that lives on these dyadic intervals, and the idea that the density for this step function for each interval, this pi is just given by the products of these beta variables. Okay, this is how it looks like in a cartoon. This is like a 3-level hierarchical beta model. Okay, you should think about that these pi's at the end of it live on a support, and pi 3, 1 is the distribution I'll give to the first interval. Pi 3, 2 is the distribution of it's like the density, it's the height of the step function for the first subinterval. This would be the height of the step function for the second, etc., okay? And how do I get these pi's? I have the idea that the parameters of the models are actually the phis. Because it's a 3-level tree, the first phi 1, 1, says what's the probability of falling in the first half or the second half. What is phi 2, 1? It's a conditional distribution that given that I'm in the first half, what's the probability of being in the first quarter, okay? And what's phi 3, 1? Conditionally that I'm deferred the first quarter of the interval, what's the probability, conditional probability of being in the first eighth of the interval, okay? So if I want to say, okay, so what's the probability of being in the eighth quarter, in the first eighth interval of this interval? It's phi 1, 1, phi 1, 1 times phi 2, 1 times phi 3, 1. And this is pi 3, 1. What is pi 3, 2? Pi 3, 2 is what is the marginal probability of being in the second eighth of the interval. So it's about the same as pi 3, 1, but at the end, I multiply it not by pi 3, 1, but by its complement, okay? So it's easy to see that all these pi's sum up to 1. And it's also easy to see that I have lots of parameters. I have 7 parameters in this model, but it's highly regularized because it's locally regularized because these guys are almost the same. And this is the idea that looks like it's lots of parameters, but it's very highly regularized, okay? And the nice thing about it that it's very easy to have a posterior on this. If I know that my data was generated like this, okay, then I can find out by the Gibbs sampler the posterior, the idea that I take this f from this like very simple tree in which all the parameters are uniform 0, 1, all the phis are uniform 0, 1. And once I see the data, I compute the updated distribution of this f. And what is it's the idea that in Ferguson's original idea, it was a conjugate class, okay? If I see multinomial observation, then the posterior of this polyetry is also a polyetry. But because I have noise here, it's not a polyetry, but it's a mixture of polyetries, okay? But it's very easy to compute it in a Gibbs sampler, okay? So this is what we do. This is the machinery, okay? Was this clear or kind of clear?
Clear.
Okay, so this is what the simulation study looks. What we do is exactly the simulation study by Candes and Sur, okay? They simulated high-dimensional logistic regression, and they have 3 exact configurations of beta. The first configuration of beta, we had 100 minus 10s 100 plus tens, and then 600 zeros. This was configuration 1. Configuration 2, all the betas were normal, were sampled of normal, 3, mean 3, standard deviation 4. And they had a third example. Betas were either half with probability, 0 with probability half, or this normal 3, 4, and normal mean 3, variance 16. And we compare 5 estimators, the MLE, the corrected MLE of Candes and Sur, and then we apply in the GLMNet either lasso with cross-validation and ridge regression, I think also with cross-validation, also our H-beta ideas. And the idea that our H-beta, all we need to think about is how many levels of the tree we use. And it doesn't really matter. I mean, as long as you use enough, we get the same result. In this case, this was like a 3-level. We have a 6-level. How does a 6th level look? It looks the same, but it goes down 6 levels. At the end, we have 65 parameters. We take the interval from 20, in this case, I mean, from 20 to 20, minus 20 to plus 20, and we cut it into 64 subintervals. In this case, so we have lots of parameters. We have like 65 parameters. No, we have 63 parameters. I mean, it should be 63 parameters. It's 1 minus 2 to the power of L. Again, we actually have 63, but they're highly regularized. I mean, the fit itself is highly regularized, okay? And in each simulated example, we run 400 Gibbs sample iterations, because at the end we have a Gibbs sample. And this is what the results look like. So what we're actually, our Gibbs sampler, the easiest thing to look at is what kind of density we have a posterior, okay? We begin, where was it? We begin with, where did I write? We begin, sorry about this, I want to show you exactly. Where did I have it? I should have it somewhere. We begin, I forgot to update. We begin with the F is H beta with hyperparameters 1, 1. And at the end, we get something like this, okay? So what do we have here? Remember case A of Candes and Sur, we have 100 minus 10s, 100 plus 10s, and 600 zeros. The green curves are the empirical CDF for this, the Oracle empirical CDF. This is what we call our beta ord, okay? We have the distribution is like 0, other minus 10. We have a point mass of 1/8 at minus 10. We have a point mass at 2 of 6/8 at 0. And we have a point mass of 1/8 at plus 10. The green is the oracle. This is what we're trying to estimate. This is a summary. The blue curves are a summary of what we get in the H beta. Remember, the H beta is not continuous, it's discrete. It is a discrete distribution, it's a step function. So these points are the step function. What are the, so we get 65 points. It should be 65 circles, okay? What do you, and this is the posterior mean. The blue curve is the posterior mean, okay? So we see that it kind of guesses the empirical CDF we want to estimate. What are this? This is like the, because we have the posterior mean, we could also think about a credible interval for the Gibbs sampler. So this is the credible interval. So we see it kind of guesses the distribution quite well, okay? So this is what we're aiming at. We want to estimate the green thing. If we would knew the green thing exactly, we could have had our base, Oracle base rules. Because we don't know how to estimate exactly, we have the H beta base rule, which are kind of not as good, okay? So this is how we estimate the coefficient estimation plot. Remember how our coefficients look? On the x-axis, we have the index for the coefficient, okay? It's actually, it looks like a curve, but it actually 100 points. So the actual value, Oracle minus 10. for the first 100, plus 10 for the next 100. And then from 200 to 800, 201 to 800, it's exactly 0. These are the MLEs. The MLEs are awful. This is the results of Candes and Sur. The MLEs for the minus 10s are too small. For the plus 10 are too big. And for the zeros, just have this huge variance, okay? This is like the initial results of Emmanuel and Paglia, okay? That the MLE is awful, okay? The red ones are lasso with cross-validation. The lasso with cross-validation actually fixes it's like the other way around. The MLEs for the minus 10 are too small. The lasso estimates for the minus 10 are too big, okay? What about the lasso for the plus 10? They're too small, okay? And for these, they're kind of okay. The blues are our posterior means. They're kind of better, I think. They're closer to the real values, but they miss by a little, okay? For the minus 10s, they're kind of too small. For the plus 10, they're kind of too big, but they're not that far off. And for the 0, they're kind of around the middle, okay? It's clear what this graph is. On the x-axis are the actual values of parameters. On the y-axis are the different estimators, okay? And this is a similar plot, but in this case, on the x-axis, we have the beta MLEs. And these are like the MLEs, and on the x-axis and the y-axis are the different estimators, okay? So the green ones, for each beta MLE, we have the actual value. So what we see here is that the places where the MLEs are very, very negative, it corresponds to the minus 10 parameters, okay? The places where the MLEs are not that small, they can either be 0 parameter, minus 10 parameters, or 0 parameters. The place where we actually have like a near 0 MLE, it's only 0 parameters. So the idea, this actually shows how difficult the estimation problem is, okay? Okay, is this clear what this graph shows? The idea that in cases where the actual parameter is small, we kind of know the places where the MLE is negative, beta hat MLE is negative, we know it's the negative guy. Here is kind of the places where we're confused. And the same here, okay? The places where the beta MLE is 0, we kind of know that it's actually 0. But the thing is, we know where it's negative or not negative, but we're not actually able to get the point. The idea is that if it's negative 10, we don't really know that it's negative 10. We kind of think it's kind of smaller than negative 10. Where it's 0, we don't have a point at 0, it's kind of around 0. And if it's plus 10, we kind of know that it's plus 10, okay? It all derives from this thing, okay? How well we're able to find the different points. And we see that the lasso is kind of, it does shrinking, but not shrinks well. So the idea that we're almost as good as the Oracle shrinker, okay? Is this clear or? Okay. And then the nice thing, I think that this is like our future work, that we do selective inference, okay? The idea is that we take our Bayes machine, and for each of the betas, we know how we have a credible interval. And the idea that our H beta credible intervals are able to cover, they have very good coverage. The idea, we only out of the 800, is this clear what these guys are? The idea, we look at each beta. On the x-axis, we draw beta hat, MLE. On the y-axis, we take the marginal credible interval for our machine, because our machine has like spews out Gibbs samplers of beta vectors. So if we look at for each beta vector, for each component, and look at the marginal credible interval, we just draw it here. Like this is like the beta with the smallest beta hat. This is like the 0.25 quantile, this is the 0.95 quantile. And what we count is how many of the parameter values we were actually able to cover. And the idea we're able to cover 792 out of 800. We're not able to cover 8 out of 800. That means that our credible our selective inferential framework is actually too good. We wanted to cover 95% of the parameters, but we're able to cover 99%, right? It's 99% of the parameters. It's about 99, right? We're not able to cover 8 out of 800. So it's 1 out of 100. So it's about not able to cover 1%. So we were able to cover 99%. Why is this so? Because the idea that our inferential scheme also incorporates or propagates uncertainty regarding the estimation of the distribution. So it's actually bigger because it also propagates uncertainty regarding the estimation of beta ord. If we would know it exactly, we'd have exact coverage, okay? For the oracle, we'd have exact FCP coverage, okay? And this is what I wanted to show you. This is how we perform for the second example. No, you remember what the second example was? The second example, the marginal distribution of beta, which I draw, in this case, beta 1 to 800, is a sample from a normal with mean 4, with mean 3, and standard deviation 4. So the green is actually the empirical distribution for the sample, and the blue stuff is what we get from our machine. Okay, and this is the third example. The third example was betas are a sample with probability half is 0. So we have this point of about half at 0, and otherwise it's normal with mean 3 and standard deviation 4. And again, the green stuff is the empirical distribution, the oracle empirical, is the empirical CDF of the oracle beta, and the blue is what we estimate. So the idea is, look, we're kind of able to figure out that we have about a mass at 0, and then we kind of mess up with estimating this. I mean, we're getting it, instead of having it like this, we're getting it like this, but we're kind of getting the general structure, okay? Look, it's a regularized nonparametric thing. It doesn't know how to guess the distribution. It does as well as it can, I mean, okay? And these are our results. This is a result for a particular one realization, okay? This would be risks. All of these are risks, okay, for one particular realization of beta. In the first example, we know what the realization is. For the beta, for B and C, we don't know what it is. And of course, we don't know the x's. So each time we simulate, we may get different result in each of the columns, especially in the last column, which is like the result from our Gibbs sampler. What we see here are the risks with relation to the maximum likelihood estimator. So the maximum likelihood estimator is very bad. The first column is what Candes and Emmanuel and Pragya are suggesting. We adjust the MLE, and we can think of estimating different vectors, either the beta vector, or the mu vector, or the p vector. So it's kind of not fair because we have the base rule for each of these configurations. So we have like, we can in our approach, we're able to estimate every parameter vector we're interested in because we're looking at base rules, and it's very easy to run them. The other things are like plugins. So maybe it's not fair. I mean, by definition, we should beat everyone because we're having a different kind of solution to everything. Not all these things are linear, okay? So that's my point. But if we go down, we see that like for each of these targets of estimation, Emmanuel and Pragya get much smaller risks. The idea that you could get much better results by either running a lasso and ridge, like look at this, for example. If we want to estimate the entire vector of beta and you use their approach, the MLE is 3 times smaller. If we use either lasso or ridge, we're able to make it like 5 times smaller than the MLE. If we're looking at using our approach, it's 10 times smaller than there. And you can see that across the board, because across the board, MLEs are bad. Emmanuel and Pragya's results are much better than the MLE because they fix it for the bias. Vanilla off-the-shelf regularization works better than Emmanuel and Pragya's result. And like tailor-made optimal shrinkage, it's better than their result. And the funny thing is that finding the oracle base, even if I know the margin distribution beta, is very difficult. The only way we can do it is by a Gibbs sampler. And when we run the Gibbs sampler, it's not much better than our results. It's not clear. I mean, by definition, it should be better. But because it's a Bayesian stuff, and these are like frequentist risks, sometimes it's better and sometimes it's worse. There's no way of actually computing these average risks, because even for one configuration of beta, it takes lots of time. So like these Bayesian approximations seem to work as well in simulations and like in my software as the actual optimal results. Okay, is this kind of clear? Or can I move on?
Yeah.
Okay, and this is the discussion. Okay, we propose general comprehensive E-based approach for large-scale inference. The idea we have like empirical basis. Usually, we want to estimate some population distribution, which no one actually knows what we're actually doing. Here, it's very simple. Our target of information is something well defined: the empirical distribution of the parameter vector. Okay, we know what we want. It exists. I mean, if you're like a frequentist, you think there is an unknown vector of beta, so by definition, it has a marginal distribution, and this is what we're aiming for. Okay, why is it general? Because it works for any problem. I mean, it may work for any problem. We haven't tried it. I mean, the idea is once we have a likelihood, we can try to adapt something. I mean, and easier said than done. I mean, what we have are this logistic regression model. I mean, this is what we have so far. Scope of application. In cases we have no previous information on the problem. Why is that? Because prior exchangeability in beta, this idea that we can look at all, we essentially look at all permutations equally probable, means that we can't use any prior information from previous experiments. I mean, we would want to, but no one does. I mean, but this is the scope of application. If you have actual informative priors, by all means use them. It makes more sense to use them. I mean, the idea, once we look at the beta as exchangeable, we have to throw out all the information we have. Okay, why does this work? Blessing of the dimensionality. Distribution of beta is easy to estimate in large scale problems. So this is one point. It works. I mean, the fact is it works. As the risk tends to be similar for permutations of beta, our methods have good frequentist properties. I mean, the idea it works because it's a high dimensional problem. Our methodology may also be used for diagnostics. The idea is you have this big problem. Let's try to estimate this marginal distribution. I mean, you may or may not be interested, but it says something about the problem. It says once we have this distribution, we could actually say something about the problem. We could say how difficult it is. How difficult it is. Let's look at the base risk. The average risk says how difficult is something, or these not. We can compute risks and average risks for this Bayesian problem. We could say how difficult it is, and we can also say compare and evaluate estimation methods. If we run our machine and it says, look, the lasso gives similar risks or average risks as our machinery, by all means, use lasso, use MLE. But if we say, look, there's a big gap, first of all, it says something about the problem. I mean, people may be interested in this. I mean, this is what the talk, yesterday's talk by Nikos was about. Let's estimate this thing for the sequence model and say something about it. By itself, it has some interest, but it also benchmarks how well we could estimate the entire vector. Okay, so by all means, we have nothing to lose by using it. If we see that our benchmarks are much better than regular estimation methods, so by all means, use our methods. If it's not, then at least you know how well you do. I mean, and thank you.